So I hope we finish that today. Let's talk about two more problems of undrained loading, two more examples. So we continue with undrained loading. When you make a hydraulic fracture, and if you make a hydraulic fracture into a very tight formation, do you think the loading here is going to be drained or undrained? So we have propped the fracture already. So when you make a hydraulic fracture, you put a lot of stress on the fracture face, and you load the rock right next to it. So let me tell you that the permeability is very low, in the order of or less than 1 microdarcy. If your permeability is very low, especially if you have fluids that are no gas, very likely you're going to go into undrained loading at the face of the fracture, because the rock is very tight. You put a lot of stress next to it, and you don't really let the fluid to escape in a short time. Do you guys know more or less how long it takes for these hydraulic fractures to be done in practice? Does it take like 1 second, 1 hour, 1 week? It is relatively fast. It's not fast as, you know, some people argue that hydraulic fractures propagate at the velocity of sound. In theory, if you were propagating a crack, and that crack was in tension all the time, that could propagate the velocity of sound, right? But here this is not the case, because you have stresses acting on the face, and the velocity of propagation is actually the velocity at which you inject fluids inside. You cannot open a fracture without fluids inside in most of the fracture. So some of these fractures, they are very, very long, like hundreds of meters, and they usually get done in about an hour or less than that. So it's relatively fast. For such a tight rock, it's a very fast loading. So here, very likely, you incur into undrained loading. And something very interesting too is the following. If you prop a fracture next to the rock, you're compressing the face of the fracture, right? What is happening at the tip of the fracture? It's tension. And if we have tension, what is going to be the change of volumetric strain? Let's assume we don't have strains in the other direction. So this tip is opening. You're creating a negative change of volumetric strain, right? You're making your rock larger at that point. So if you do that, what would you expect? In this case, you compress this undrained loading, and similar as before, you increase the pressure. At the tip of the fracture, you create a negative change of pressure. There are some people that actually they argue that you can take the fluid into cavitation at the tip of the fracture. I don't know if you can get to there. In theory, you could, right? But I don't know if in practice you get that far. But definitely, if you have a dilation, you're going to have a negative change of pressure. And let's go to one more example. Some of these fractures also, let me try to see the best way of plotting this. So this is a horizontal wellbore, okay? And this is what is called the toe. This is the heel of the wellbore. It's a wellbore that it's getting into the screen and turning horizontal there, in which you are creating some hydraulic fractures, and that's your minimum principal stress in that direction, which in this case should be horizontal. So there are some people that are starting to place gauges here in around other wellbores that they will use later on too, in order to predict what is the change of pore pressure because of undrained loading, because of placing a fracture near that point. So in theory, if you get a fracture that goes near this point, or if it goes through, you could tell if that one went through by measuring the pore pressure there. You could also measure things as a little bit, it's more difficult, but you could measure displacement, temperature. But now this is a new type of fracture diagnostic that allows you to see if there is something approaching by measuring the change in pore pressure in the rock itself because of undrained loading. Another version of this is something that I was trying to work on, but didn't get my proposal funded, is to monitor undrained loading. If you were to inject fluids in a formation, in theory also you could place pore pressure transducers along the wellbore that will tell you how much the pore pressure changes there, in order to predict if in this case was for carbon dioxide injection, if it's approaching or not. Because it's very difficult on the subsurface to see if fractures are getting to a point, if fluids are getting to a point, because you can't see that. You can do 4D seismic, but sometimes that's expensive. You could do acoustic emission, something we're going to get later on to, but that also, it's much more complicated than just measuring pore pressure. But based on undrained loading, in theory, you could measure these changes of pore pressure because of changes somewhere else in the formation. Okay, so let's see the equations that we need in order to solve that problem. Before I do that, I'm just going to check quickly the game Argentina-Brazil, okay? It's going to be 1 second. I'll take some water. Still 0-0. Okay, good. It's in theory it's a friendly match, right? But there is no friendly match with Brazil. No, no friendly match. No. Okay, so the first thing that we're going to do here is to write the equation that describes a pore pressure change due to volumetric strain. So basically, what we want to know is, with perfect undrained loading conditions, what is going to be the variation of pore pressure with the variation of volumetric strain, knowing that density times porosity, the change of density and porosity is equal to 0, also known as undrained loading. I'm glad that we're still 0, 0 because this is a new group of guys. It's not the old guys. No Messi, no nothing, right? Okay. So, okay, this is constant. I thought we'll be losing like 3-0 by now, but we're not. We're not. Okay, so the schematic of this equivalent representation will be a porous medium, and we're applying a volumetric strain. We're compressing the rock, we're compressing the fluids, we're compressing everything. And I hope that you can run the experiment in your head and see that the pressure is going to increase if we don't let the fluid come out. So in order to solve that, what we have to do is we have to use this equation that we have over here. That one. Basically, we want to know what is the variation. Let me delete this P that we weren't using P for elasticity. We want to know what is the variation of pressure as with the variation of volumetric strain. And in this case, we can forget about the time, and we can also forget about space. And basically, the ratio of this one to that one is just going to be minus alpha, the VL modulus, where we know that what VL modulus is, we wrote that before, is going to be alpha minus the porosity Ks plus porosity Ks divided by Kf. So if we know what is the VO coefficient, if we know what is the porosity, and now notice that we have the compressibility of the solid, that we can also express as the bulk modulus of the entire rock as we did before, and the compressibility of the fluid, we can calculate what that's going to be, what that value is going to be. Notice that this one is going to go into the other side, right? So the bigger the bulk modulus of these two, and especially of the fluid, the bigger the increase of pore pressure is going to be. Okay, so that's the first problem. The second one, it's a similar type of loading, but what we want to calculate is what is called the undrained bulk modulus. So basically here, we want to see what is the increase of mean stress required to deform the porous solid a given amount, but without letting the fluid get out. When we did let the fluid get out, the variation of mean stress with variation of volumetric strain, if we had this rock either drained or if you did this dry, it will just give you K, which is the bulk modulus. Of the porous solid. This is the same K that you had that you figured out from the experiment I gave you. The slope of that curve is that K. Well, we could also run a similar experiment, but now we do not let the fluid get out, and the variation of mean stress is the same equation, but now this is going to remain constant, which is undrained. And in order to do this, what I'm going to do is I'm going to call this KU, and we're going to find that right here. Okay, but just let me call it Ku. That's undrained bulk modulus. If you remember from our equations of poroelasticity, we had that mean stress depends on the deformation of the solid, volumetric strain minus alpha p. Therefore, a variation of mean stress with variation of volumetric strain is going to be K minus alpha variation of P. The pressure is going to increase, as we saw before, with volumetric strain. And actually, we already have that one over there. You see, it's alpha times M. So this is going to be K minus alpha BL modulus, and therefore the undrained modulus Ku is going to be K plus alpha squared times BL modulus. And this one is Ku. Notice that as it makes sense now that the undrained bulk modulus is bigger than the drained bulk modulus, because now you are also compressing the fluids inside the rock. So if you needed to do a problem of elasticity in which you need to calculate deformations, but there is no fluid going out, this is not what you need. Or you can use the whole theory of poroelasticity and use this, or use directly this undrained bulk modulus. That will be the equivalent bulk modulus of a fluid, which is of a porous medium, which is saturated with the fluid. And our third example is going to be one more version of undrained loading. All of these are it's the same problem. We're just looking at different applications or different parameters in the problem, right? First, we looked at how much pore pressure would increase if you have undrained loading. That's the pore pressure that, for example, you will have to, that you will need in order to design transducers that will go in here or into there. In order to measure a pore pressure change, you want to design those to capture more or less what you want. Undrained bulk modulus that you will need in order to calculate strains if you have a fluid which is not a porous medium which is not letting the fluid escape. And the last one is what is called the Skempton's parameter. And the Skempton parameter, it's a parameter that tells you what is going to be the change in pore pressure in a given fluid saturated porous medium given a change in mean stress. So it's the same experiment, but instead of imposing a volumetric strain, now you're imposing a change of mean stress. And you want to know what is going to be the change in pressure. If you had a porous solid in which the compressibility of the fluid is much lower than compressibility of the solid, all of the increase in mean stress will go into increase of pore pressure. But if you have a porous solid in which it has a solid with a lower compressibility, then that load is going to divide. How much? That's what the Skempton parameter is going to tell you. So we're going to define this as B. This is the Skempton parameter. We're going to work again through our poroelasticity equations. And this is going to be alpha P. So now look, we want to take derivatives of this with respect to pressure, which is the inverse of that. And this is going to be, this is a constant. This is derivative of volumetric strain with pressure. And this is going to be just alpha. And we know this guy from the previous equation where it's up right there. It's that one, right? So that one is going to be 1 over alpha m minus alpha. And from here, we'll get the b is going to be the inverse of this. So alpha plus k alpha m inverse, right? And that's going to be the Skempton parameter. And I have simplified that a little bit more here in my equation. Let's see what I did. So I took the alpha out. And you can work these equations to look like this. And that's the Skempton parameter. The Skempton parameter is very useful in experimental geomechanics because it lets you know when a rock is fully saturated or not. Let's imagine that we go to the lab and you run an experiment in which you saturate a rock or a sediment with a fluid, you put the membrane, you increase the confining pressure, which in this case is going to go into increases of mean stress from all sides. And when you do that, you have a pipe that comes out from here in which you have a gauge that it doesn't let the fluid go anywhere. So this one is closed. And you want to measure what is the increase of pore pressure by adding stress. Well, what the Skempton parameter tells you is that when the Skempton parameter goes equal to more or less 1, or it approaches 1, your rock is saturated. When B is much less than 1, it means that there is some gas in the pore space. So let me see how much time I have in order to explain this. We said we had to discuss something, right? What was that? The abstract or something else? The exam. Yeah, the exam, the old exam. Okay, well, I'm going to try to finish this very quickly. But the whole idea here is about this Skempton parameter is that, let's say that we know alpha, and it's about 0.9, okay? So we know that value. But what is really important here is this ratio. That ratio, you can write it as K alpha minus porosity divided by Ks, and K porosity divided by Kf. So if your bulk modulus is much smaller than the than the skeletal modulus, like for example in soils or uncemented sediments, and your K is also much smaller than your KF, then your BO coefficient should tend, this is going to be, it's going to be 0, right? This is going to be 0, this is going to be 0, and your BO, your Skempton coefficient is going to tend to 1. And whenever in this relationship, if you have gas present inside the porous medium, the compressibility of the fluid is going to actually be very small. It's not going to be that high. If you have water, this is going to be very high. If you have a gas, this is going to be very low, and then your Skempton coefficient is not going to be 1 anymore. Okay, all right, guys. So I think we're done with the pore elasticity part. I'm going to upload this page later on, where you can see a summary of, before we had seen the BO coefficient as function of permeability and porosity. Now we have undrained bulk modulus of the solid, and Skempton parameter BO modulus also in here. So you can understand a little bit more about how those vary for different conditions. Yes?
That's a dumb question.
There is no dumb question.
So how is it possible that the bulk modulus is smaller than both the solid and the fluid?
If you have uncemented sediments filled with water, the bulk modulus of the sand and the elasticity of the sand is going to depend mostly on the contacts. So these contacts are going to be much more deformable than the solid itself. So in there, you will have already your K much less than the Ks. Typical bulk modulus of a sand are in the order of 0.1 gigapascals, while the bulk modulus of the solid is in the order of 30 gigapascals. So 0.1 to 35. And if you have this sand saturated with water, also your bulk modulus 0.1 gigapascal is going to be much smaller than the 2 gigapascals, which is the bulk modulus of the water.
So you can't view this as a two-component mixture and calculate based on any sort of mixing rules?
No, because you still have some finite bulk modulus of the sand that depends on the elastic part of the. This is drained.
This be under drained conditions?
This is in undrained condition.
So I guess what I'm trying to get at is that if you have undrained condition,
Yeah.
So you can view your bulk as the two-component mixture of the solid and the fluid.
Yeah.
So why wouldn't the entire bulk modulus be somewhere in between?
I think I see where you're getting into. You'll be close to that, but with all those mixture equations, many times you have to assume a shape of the pores, right? For example, if you assume spherical pores, then those have to be far apart from each other, and then you have to solve the Kirsch equation around those in order to come up with an equation for that. In this case, you will have to account for the elasticity of the contacts in order to solve for that K. Hamza, you have a question or a comment?
I was just going to say that like bulk modulus for water is changing from flow divided by the volume of flow multiplied by the total volume. And of solid is changing the volume of source divided by the volume of solid, not total volume, while bulk volume is
The total volume. Correct. Yeah. 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 I think you can use some mixing equations, but you just get some upper bound and lower bound, which are not going to be really the actual one that we're calculating
Any
in
upper
here.
lower bound will be.
Yes. Yeah. Absolutely.
But I see your point.
Absolutely.
The mixing rules will break down after you
Yeah.
have larger pores and if they're closer to each
Yes. All right. Okay, guys. Let's talk about the exam. What questions do you have? Would you like me to pull the exam from here and we take a look at it, or you have some specific questions?
Can you tell us kind of up to what point the exam?
Up to here. Okay?
Here?
Yeah. Up to here. Yeah. So everything up to now. So again, I don't want you to memorize these equations. Probably I like that you know how more or less how to derive those, but to me it's more interesting that you know the meaning of the equations. For example, I gave you in the previous exam, I asked about the meaning of I guess these equations. So probably you have to tell me what this means, what is variation of pressure with time, this is variation of pressure in space, this is variation of volumetric strain with time. Probably I could ask something more specific about that, but for example, let's look at the undrained bulk modulus. Why is the undrained bulk modulus bigger than the drained bulk modulus? Because you have the fluids inside, and that's actually quantified by that term over there. Yeah, John.
So 2 questions. So in the diffusivity equation with the coupled poroelasticity, is the K term there permeability or is it bulk mass?
This K over here is permeability.
That's permeability.
Yeah, because it came from Darcy equation. That's permeability, yeah.
And then, so what physically is the BO modulus describing?
It's,
I know like the BO's coefficient is like a correction factor for the pore pressure, but does the BO's coefficient actually relate to something?
so, well, the BO modulus is taking into account not only the compressibility of the porous medium itself, but it's also taking into account the compressibility of the fluid. So it's sort of a compressibility coefficient of the entire porous medium together with the fluid. In most equations, for example, if you were to derive equations of diffusivity equation with no variations of porosity, all your compressibility will go into compressibility of the fluid. But now, with this poroelastic derivation, we have both. And those are also kind of quantified according to the porosity.